Welcome to this session on multi-strain modeling. Our first speaker will be Dan Harborn from the University of Nottingham. Thank you very much for coming and look forward to your presentation.
Thank you. As Josh said, my name's Dan. I'm from the University of Nottingham. I am a mathematician, and I'm not ashamed of it. So the flavour of my talk is going to be a lot more theoretical than a lot of the other talks we've had so far. Please don't let that put you off. I promise it's useful and it's interesting to me. Okay, so I was tempted to call this learning objectives because I used to be a teacher, but I haven't. So I'm just going to talk you through what I'm going to talk to you about, and then I will dive straight into it. So firstly, I'm just going to give you an overview of what A, my talk, and B, my current project is about. Then because I'm not expecting everyone here to have a bachelor's degree in mathematics, I'll talk you through the preliminaries and basically talk you through how I would build a mathematical model of the type I'm going to show you. I'll take you through my model, which is the one I'm currently working on, and then into this stochastic averaging, which is some fun words, which is where I'm going to drop some really heavy maths on you and leave you all baffled. But don't worry about it. It's more about grasping the broader ideas and the finer points. And then I'll talk to you, and then I'll do a brief slide on where I'm then going to sort of take this in the future. Okay, so we're going to start with what my project is about, what it is and why we would want to study it. So in mathematical modeling, it just allows us to build very general and very flexible representations for various phenomena. In this context, we're looking at disease modeling. And then there's lots of different techniques that we can use for building mathematical models, and there's lots of different types of mathematical models we can use. The two that I mostly look at are deterministic ODE models and stochastic Markov chain models. So the difference between deterministic and stochastic, for anyone who just needs a refresher or maybe just doesn't know, stochastic means involving randomness. Deterministic means the same every time, very simply. Why would we want to use stochasticity, which is a difficult word to say? Well, in real life, things don't always behave in exactly the same way. And so we don't generally, when we plot data from real experiments, we don't see perfectly smooth curves. So in that respect, sometimes it can be helpful to increase the realism element of a model to introduce some element of randomness as systems evolve. And then what I'm going to talk about, sort of the point of my current work, is looking at a particular model reduction technique. So when we build these big models, we might have 4 or 5, even more dimensions, which becomes very quickly very difficult to talk about in a mathematical context. So very common thing to do is use things called model reduction techniques, where we essentially decide which variables we like and which ones we don't, rip them out, and give ourselves a simpler model. So the way this talk is going to run is we're going to talk through building my model for representing a disease with multiple strains or 2 different diseases in the same population. We're going to apply the stochastic averaging principle to obtain a reduced model, and then verify that the models agree in the large number limit. If any of that made sense to you, brilliant. If it didn't, don't worry. We're going to go through all of it. Okay. So firstly, as I said, we're just going to go through the preliminaries, which is where I'll just show you how I would build a mathematical model. And I'm going to do it on the simplest model that we have in mathematical epidemiology, which is called the SIR model. Most people will probably be somewhat familiar with this. Whether or not you've seen it in a maths context is another thing. But basically, we build it like this. We have this lovely flowchart where we have 3 compartments. This is a compartmental model. We have 3 compartments where our different members of our population fit in. So we have susceptibles, which are the people who aren't sick yet, but can become sick. We have the infected, people who have it, and people who are recovered. So the people who did have it, don't anymore, can't get it again. This is the simplest way to do it. This was first presented in 1927 by these 2 guys, Kermack and McKendrick. And from this, this has then become sort of the basis for all sort of further mathematical models that we've built on top of it. Okay, so this is what an ODE model would look like. And I've kept my lovely flowchart up at the top there so we can sort of see where it all comes from. So the way it works is I'm looking at basically how things move from the compartment. So I see that things get infected with beta Si up there. And so what's happening when something goes from susceptible to infected is it leaves susceptible and goes into infected. So that's where these two terms come from. So we have a minus on the S equation and a plus on the I equation. So we lose one and gain one. Okay, and same thing happens for the other terms. This is the basic building blocks of how we would put together an ODE model. Okay, these are one of the most common tools for mathematical modeling, particularly deterministic modeling, because their theory is well understood. And as you can see from sort of how we put this one together, it's very modular. We can add and take away things as we like. But then, of course, the drawback, as I said before, is these are deterministic. And determinism doesn't always capture all the information that you want it to. So we can also use some, and if I plot the solutions of the ODE, it looks a bit like this, okay? And you see we have these very smooth curves, but as I said, we don't generally see smooth curves often in real life. So we want to use some different techniques, particularly something called a continuous time Markov chain. And this is just a way of accounting for randomness. Now, this looks pretty horrible. Don't worry about it. It's exactly the same information as we were putting into the ODE. So we have, I lose one, I gain one when something gets infected. And I have, lose one, gain one. And this is all information which is encoded in this thing called the generator equation, which is that horrible thing looking at the end. Okay? It's exactly the same not formulation, it's exactly the same kind of base structure, but now instead of thinking about a smooth curve going continuously through a time interval, instead we've got small time intervals where we're expecting things to change according to some probability. Okay, so we build it with these things called a state vector, which is keeping track of how much everything has. The intensity functions, which in this context is sort of the probability of having, so the first one would be probability of something being infected, and then the second one would be the probability of it recovering. Okay, and then all of that information is just encoded in this big equation at the bottom. And we see that when we plot this one, we don't have those smooth curves anymore because we've accounted for this randomness. So we've got this sort of random time change. Okay, so a big part of my research is looking at how these two types of models interact and at what kind of times we can say they look the same. So there's this theorem called Kurtz's theorem, which I will spare you from because it looks horrible, which says that as long as our representations, as long as our equations fulfill certain conditions, then we'll have, as we make the system very large, as we go into a very large population, we'll have that our stochastic model, all those big fluctuations, will get smoother and smoother. So even just going from a size of 100 to a size of 1,000, we've massively smoothed out our stochasticity, our randomness. Okay. So with all that in mind, I'm going to talk to you about the model that I'm currently working on, and we're going to build both the ODE model and stochastic model in exactly the same way. So this is what my model looks like. This is a two-strain model. So it's an extension of our basic SIR, but now instead of just one nice flow chart, we've got these two kind of circles, okay? Or these two triangles, I suppose. So we have two different strains. We assume that there's a common pool of susceptibles. So we have two different strains that are going through the same population, or two different diseases that are going through the same population. We assume no co-infection, which means we can't have somebody who has both diseases at the same time. And then we also assume partial cross-immunity. So it's if we are either infected, if we are recovering from the second strain, then we can't get infected with the first strain. But if we are infected with the first, if we were recovering from the first, we could be infected by the second. Okay. So this kind of two-strain model, this kind of extension to the basic SIR model, comes from early studies of influenza, bacterial infections, parasites, things like that. That's where you'll find kind of the first uses of these kinds of model in the literature. And of course, more recently, don't know if anyone noticed, there was a pandemic a few years ago, and that became very interesting. Where I originally found this to start looking at it was in a paper which talked about the emerging strains of COVID, so the Delta and the Omicron variants. Okay, so again, we'll talk through it. We build it in exactly the same way. It now has just a few more bits, but if we look at basically the arrows, we'll see that it's exactly the same building blocks. So I'm leaving S and going into I1. So I have a minus on the S and a plus on the I1. Okay, and it's built exactly the same way. And then if I just look at the I1 in isolation, all the terms that come after the equal sign are just everything that's going into or out of that blue dot. Okay, and this is why I introduced the CTMC model on an easier example first, because just showing you that would be scary. But it's exactly the same building blocks. So again, if I look at my beta 1, so how we're getting infected with this first strain, that's just one of the intensity functions there, which is essentially, in this case, the probability of that infection occurring. Okay, and all of it is handled encoded in this big, horrible generator equation. So we've got that minus E1 and that plus E2. That means we lose a 1, which is the S, and gain a 2, which is the I1. Okay, and if I plot the solutions to both my deterministic and stochastic models, Kurtz's theorem gives me that as I make it a bigger and bigger system, my stochasticity will reduce, and I will get to a deterministic limit. Okay, so now I'm going to get into the genuinely heavy maths, so don't worry too much, just try and take in the broad strokes. So with this model reduction problem, something we're interested in is to look at a scenario where the rates of infection and recovery of one of the strains is considerably faster than the other. Okay, so in this case, just arbitrarily, I'm going to pick the second one. So my big red arrow just means that is my really fast strain. Okay, by assuming that one is much faster than the other, we can then implement this model reduction technique called the stochastic averaging principle in order to give us a reduced model. Okay, and some reasons why we might want to look at models where we have one strain acting much faster than the other. Examples in the literature include things like tuberculosis, vector-borne disease, illnesses and STDs, certain types of cancer therapy, and strain-specific vaccination. So anything where we're looking at something that's already endemic, and then we bring in something that's incredibly virulent and acts very, very quickly. Okay, so heavy stuff now. So the way that we apply the averaging principle is essentially we play about with our parameters. So we play about with all these rates, all these letters that I've got up on my diagram. Okay, in order to make one strain much faster than the other from a maths perspective, what we've got to do is, well, literally, we make the numbers bigger. So if I look, if I'm saying my second strain is the faster one, for all my ones with a little 2 subscript, I've multiplied by n, which is our system size, so how big our population is. Okay, so if we have a big population, say 10,000, then the second strain is acting 10,000 times faster, essentially. Okay, we then make a scaled process, so we change our CTMC model just slightly to reflect that we've got fast and slow. So again, my first 3, my S, my I1, and my R2, that's a typo, my R1, they've all got a 1 over n because they're now the slower variables. My I2 and R2 don't have an n, or they are n times larger than the other ones because they're going at a much faster time scale. And then I rewrite my intensity functions to make them simpler. And yes, I am saying that with a straight face. And we get this generator. Okay, again, Minutia, not important, but all we need to know is that this big equation captures all of the information about how this system evolves. Okay? So the way that that generator is structured gives us that, from a stochastic perspective, that the infected and recovered variables of the second strain are going to jump rapidly. Because they're happening on a much faster timescale, we're going to see big, big jumps. And those of the first strain are going to have roughly deterministic dynamics because the variations are so much smaller. Okay? And then what we're saying with the stochastic averaging principle is, therefore, because these fluctuations are so much better, what we're going to do is we're going to use the average dynamics of my big jumps in order to then reduce my equations. Okay, so we just make a new operator equation, a new generator equation to describe just the fast process. So all I've done is taken all the terms in this which have a fast variable in them, and I've made that its own equation. And then this operator, this fast operator for these fast equations, gives me something called an ergodic Markov process, which admits a stationary distribution, which, long story short, and cutting out a lot of heavy maths, gives us our average values. Okay, and so what we can then say is that my slower variables converge to a deterministic set of variables, which is then written as this ODE, which now has only 3 variables. So everywhere we had an I2 and an R2, we've replaced with its average. And let me just get me to where I am. We've replaced it with the average values of the fast process. And so, because equations are only so helpful, I'll give you some pictures as well. So if we were to plot the solutions to this, so this is our reduced system. So this is, the dotted line is the solutions to these equations. Ooh. And the solid lines are the solutions to the CTMC. So what we see is, if we look at the top one with the purple and the red, we can see really big fluctuations, really big changes, because it's happening on a much faster timescale, much greater expression. And then just on the top one, if you look just as that randomness count stops and goes to 0, we see the dotted lines coming through. That's the average of those big fluctuations. Okay, so we see that as we increase our system size, our fluctuations are getting smaller and smaller, and our Markov chain model follows the solutions of our reduced ODE much more closely. Okay, so deep breath. I'm aware I just dropped an awful lot of maths on you there, but this is what I do. I find it interesting. But places that we could go with this next, the places that I've planned to go with this next is, first of all, this work that I'm working on right now is hopefully going to be my first paper. And so getting that published is kind of my next main step. In the slightly longer term, when we look at these fluctuations, these big fluctuations, we can actually write equations that tell us how those behave. So we can write an equation using something called the functional central limit theorem, which will give us an equation that describes how those fluctuations reduce over time and as we increase the system size. And then finally, in the longer term, which is more just my supervisors know a lot about it and think it would be fun, we want to investigate applications of large deviation theory. And then reach the end. So I have to acknowledge my supervisors, who without them, I would not understand a word of what I just said. And also have to thank my girlfriend, Vicky, who is much better at making PowerPoints than I am. And of course, thank you to Jason and to all the organizers for the last few days.
That was great, Dan. Thank you very much. Any questions?
Hi, that was absolutely fantastic. I come from a math background as well, so seeing some ODEs made my heart sing.
Thank you.
Would you plan on using these models for projections or intervention testing, or is it more just looking at fun generators?
So, great question. So we can use it for predictions, and indeed, in the early days of COVID, a lot of these kinds of models were used for predictions. My work specifically isn't concerned with that because I'm far more on the sort of purer side. So a lot of mine is to do with, so basically the brunt of my paper that I'm working on is essentially proving that I can do this model reduction. But no, absolutely. Models of these kinds are absolutely used for prediction, and we can also use it to look at the efficacy of things like vaccination. So we can look at, so because the models are so modular, we can add and subtract things as we like and look at what happens as we change different parameters depending on the situation.
Great talk. When looking at the results, the averages versus the stochastic fluctuations, and you kind of touched on this. What do you think some of the policy implications might be when considering that there's errors in the two different, in the two different trends?
Sorry, could you repeat that?
If you can go to your slide with the trajectories.
Oh, I'm holding the wrong thing.
Yeah, so you have your stochastic fluctuations, and then you have the stochastic averages. What do you think some of the policy implications might be? If the stochastic fluctuations compared to the averages there's going to be, an error involved, right? So what do you think some of those implications might be in terms of making policy? I know you did just touched on that.
Yeah. So in terms of making policy, I'm not sure I'm qualified to say, but in terms of the error, so essentially, what I've used here is relatively small population sizes, basically in order to show the difference between as I go up by just a factor of 10. And as you say, the error, which would be kind of the next work. So this is the FCLN, functional central limit theorem, that quantifies the error essentially. And we can show that if our model meets the right conditions, then that error will become, well, not zero, but very, very close to zero as we get larger.
Not a mathematician, so I appreciate the hand-holding. So I hope this isn't too naive, but you've got, you're looking at the stochasticity with these generator equations. Do you use one matrix across all compartments? Or is there ever a reason why you might, I couldn't work it out from the equations, is there a reason why you might have separate matrices for each compartment to consider, to study sort of confounders and the interdependence of stochasticity in the system?
Good question. It's not something I'd considered because basically the way that we study the stochastic dynamics is we plug it into a thing called the Gillespie algorithm, which just updates it as a single row vector or a single matrix. So I wouldn't be able to answer informedly.
I feel like there's like a lot of problems where we only observe the slow dynamic, but we have questions about the structure of the fast dynamic.
Yes.
And I wonder if like you can comment on like, does this help you kind of understand when that problem is actually solvable and when it's not? Like if I have a question about, say, like I'm observing the slow, some function of the slow trajectories, but I am curious about like some parameter of the fast trajectories. Is that can you comment on the solvability of that problem?
Yeah. So from a deterministic perspective, the reason that we want to use a lot of these kind of model reduction techniques is because bigger models, so even just the one I showed where it was 5 different equations, that is sort of intractable to analyze from a sort of algebraic perspective. So we can't, it's really difficult to write it down in a way. So yeah, this model. So the way, from a deterministic perspective, this model reduction would work is we would look at what happens close to like in the fast time area, essentially. So we look very close to start time. We come up with a solution there. We come up with a solution in the later times, and then we sort of stitch them together to make a composite solution. So yeah, so in that way, we can look at the dynamics on the fast time scale, and as they then go into the longer time scale. So I think the interesting thing for me about that is essentially being able to almost handle weird I'll get my train of thought back, I promise. The interesting thing for me is how we can essentially make something that wasn't solvable by cutting it into pieces and then putting it back together again.
Hey, great talk. I just wanted to ask a quick question about sort of the methods used for numerical integration here.
Yes.
Thinking, why one would want to use a CTMC style integrator versus, say, like a more standard stochastic ODE, like an Euler Maruyama sort of approach, and the sort of general benefits of one versus, or of using a method like this.
Yeah, really nice question. So if I go back to my big horrible equations, if I look at a CTMC with a generator equation, essentially the reason that this is a good way of talking about it is because that equation captures all the information about the Markov chain. And it's not entirely obvious here, but we can actually rework this as a stochastic PDE. We would turn this just into a Kolmogorov-Ford equation. So it's entirely just because this representation as written is, and I say this again completely straight-facedly, this is a very neat way of writing all the information about our Markov chain.
Great. Well, let's thank Dan one more time. Great talk.